All right, so in our first video on capacitors, we're just going to try to figure out what they are and what are the important units of measurement in capacitance. So as I described in the last video, capacitors are super important because they take that AC rectified current, that red one that you see here, and they trickle in current so that it kind of mimics a direct current. I talked about how devices often need a minimum voltage. This is voltage. Let's imagine my device needs 120. If the current goes below, or the voltage goes below 120, it turns off. So capacitors are super important. They trickle in, they're like mini batteries that trickle in voltage when my AC power goes down below that threshold. So these here are different types of capacitors. You have some really small ones. If you open up any electronic device, these are probably the most dangerous parts of your electronic device because they store charge. And if I was to touch two sides of this, I will get shocked, okay? So your mosquito zappers, those tennis racket zappers, use capacitors, and they store charge on two different metal plates. And if a mosquito gets in there, it zaps itself because it connects the two ends. So think of these as mini batteries that are storing charge. So this mini battery will be connected to your circuit such that when the voltage goes down, it then starts to discharge its charge into the circuit. So the capacitor is supplying a current up over here, or supplying a voltage. It's a mini rechargeable battery, okay? And what we're going to be looking at in this video is to understand the structure of capacitors and how it relates to the formula and how they work. We'll define what capacitance is. If you see on these devices, they all have different numbers. 4,700 micro F, 35 V. So that means at 35 volts, this capacitor is 4,700 microfarads, which is a unit of capacitance. It's storing charge. 100 microfarads, 16 volts. It tells us all the operating capacity of these things. Okay, so we'll learn what capacitance is, and we're going to try to understand why they look different. What are the factors that affect capacitance and the amount of charge that they store? Not difficult stuff. Here we go. So the invention of capacitors goes along with the invention of a battery when we discovered batteries. If I connect electrical potential, okay, like a battery, to two parallel metal plates, these are two metal plates that are separated by air. The plates are going to store charge, and if I slowly bring these plates closer and closer together, eventually a spark is going to jump. So in our original discovery of electricity, we were playing around with capacitors right from the beginning. We were attaching them to chemical batteries, and what we noticed is when we bring them to the two plates close together, we get a spark. Okay, so a capacitor is a type of device that stores charge on metal plates, but the charge does not flow through. It's just getting stored. So this battery is putting charge onto these plates and creating a mini battery. So a capacitor, again, is two metal plates separated by a distance. And the role of the capacitor is to store charge, like a mini battery, okay? So just to go through this diagram again, I would have a plate up here with an area, a plate down there, metal plate with an area, separated by air or another material that's not conductive, so that those charges can be stored. And the reason why this is positive is it's connected to the positive terminal of a battery. That's connected to the negative terminal of a battery. And when that charge flows onto these plates, you guys have done this for a very long time, an electric field is generated between those plates such that, remember, it goes like the arrows will look like that. Now, this electric field is uniformly spaced, so I have a uniform electric field, and I'd have these end caps as well, okay? And my electric field strength is related to the voltage that's being applied divided by the distance, okay? That's just a reminder. So if I was ever asked to calculate the electric field between these two parallel plates in a capacitor, I just have to take the voltage divided by the distance, and that's my electric field strength. That would be the force experienced by a charged particle in between those two plates, okay? So off we go. So how do parallel plate capacitors, this is the structure of, if you ever see two parallel lines, that is a capacitor, okay? How do they work in an AC circuit? So here I have an AC source. Remember the voltage is going to change from positive minus to minus positive. It's going to fluctuate. And this little device that I have here, this device that I have here is a diode, okay? So if I put a diode and I constructed a circuit that looks like this, only the positive current is going to flow through my load. This is a load over here. Okay, so imagine that's the screen for your computer, okay? My screen always needs positive and negative, okay? Otherwise it won't work. So my AC current is flip-flopping. Only when it's positive does a current go through here, my screen turns on. That's that green little hump over there. So if this is voltage over time, okay, that my screen would turn on, turn off, turn on, turn off, turn on, turn off, okay? The capacitor is put in parallel because what happens is as soon as my AC current turns on, my AC current charges my capacitor at the same time as supplying the power to my load. So as the AC is flowing through here, the current is flowing through here, it's charging my capacitor, and it's also supplying a voltage to that load. So it's on, and as soon as that voltage goes down, instead of the device turning off, well, now this battery has been charged, so the current can then flow and slowly leak into my device, and over time, keep it on. So my capacitor is being charged, it's storing the charge, and then when the voltage goes down below the threshold, the battery takes over, the capacitor takes over and supplies the current to my load. It's a smart little device. So the more of these capacitors I have in the circuit, the longer I can keep that charge trickling in. So if this was just one capacitor, in reality, I would imagine it would go down really, really fast. So we probably need quite a few capacitors in there to keep this load feeling the charge when my AC current flips directions, okay? So that's how a capacitor works. It's in parallel to my AC source, and it stores charge, and it's used to trickle charge into a load when the AC current goes negative or below a threshold. That's my capacitor effect. All right, so how does a capacitor really work? Well, we need to learn a few terms. The amount of charge that can be stored on that plate, which is really important. The more charge I store, the more effect I will have. Okay, so the more charge I can store, the better, but the amount of charge that I can store is limited by the word capacitance. You guys got to memorize a definition here. So capacitance is the ability of this parallel plate to store charge, this parallel plate. So what factors affect how well that parallel plate can store charge? The more charge I can store, the better. So capacitance is defined as the total amount of charge that that plate can store per volt that I apply. Okay, so for example, if I had a capacitor that is 10 F, well, what is F? F is a farad. That's what it says down here. A farad is a unit of capacitance. So 10 farads means that my parallel plate can store 10 coulombs of charge per 1 volt applied. So if I go back up here, if my battery is 1 volt, this can store 10 coulombs of charge. That would be an incredible amount of charge for 1 volt. Okay, that's very, very high. All right, so a 10 farad capacitor is incredibly dangerous. It stores a lot of charge. Okay, that's very important for you to know. So if you ever see a component that is not micro but is big farads, don't go near it. You'll get electrocuted. Okay, so Q is the charge on the plates, V is the voltage applied. So if I apply a voltage and I'm able to measure the charge, if I divide them, I can calculate the capacitance. On the other hand, if I know the capacitance, 10 farads, and I apply 100 volts, 100 times 10 tells me the charge that is being stored. Okay, so 100 volts times 10 farads is going to be 1,000 coulombs of charge. So I can play around with this equation now. You have this equation in your data booklet. Okay, so quickly stop right now, open your data booklets, and take a look for all the formulas in electricity that have a C. Those are your capacitance formulas. So capacitance times voltage gives me the total charge stored on a device. Charge divided by voltage gives me the capacitance of that device. And charge divided by capacitance gives me the voltage that is applied to that device. Okay, so that's just your step number one, making sure you know how to apply this formula. Then let's take a look at how can I increase the capacitance, that C value of a capacitor. So what are the actual structural properties that affect how much charge can be stored when I apply 1 volt? Okay, well, in a capacitor you have area, you have the distance separating the plates, and you have a material that keeps those plates separated. If they connect, they're not a capacitor anymore. The current flows through, so we need to keep them separated. And that material that keeps them separated is called a dielectric. It's a material that allows a field to be generated, okay? So any type of polar material. I can even put air or a vacuum in between. That's a material that keeps them separated. But that will affect how much charge I can put on these plates. So here is just a cross-section of it. I got plate 1, plate 2, positive plate, negative plate. Here's my electric field. These little plus minuses are the molecules in my dielectric, polarized molecules. So it's like a material like a gel or paper or air, okay? Ben Simpson did his IA on this, and he was looking at how salt affects capacitance. So it was a great IA where he changed that plus minus in there and took a look at the performance of capacitors. Okay, so again, capacitance depends on the geometry. And here's the formula, another formula for capacitance that tells me how the geometry of this affects that C value. C is charge over voltage. The higher the C, the more charge I'm storing on that capacitor. So this value here, that E, is my dielectric. Okay, it's the polarity of this. So everything has a dielectric constant. Air has a dielectric constant. Vacuum has a dielectric constant. In fact, vacuum is just the permittivity. We've seen this thing before. Permittivity of free space, which you have in your data booklet. Okay, so as long as if they ever say that a capacitor has a vacuum in between it, then you use the permittivity of free space, or you'll use the dielectric of air, or whatever material they tell you, they'll give you the dielectric. So capacitance is directly proportional to the dielectric, okay? The more polar the molecules are, the higher that dielectric constant gets. So the more capacitance I have. The greater the capacitance, the greater the charge. Beware, in multiple choice questions, they love to play that game. They say, I put a material in there that has a higher dielectric constant. What happens to the charge on the plates, or what happens to the amount of charge if I increase the voltage? What happens to the graph? You should be able to understand that. It's directly proportional. Likewise, if I increase the area of the plate, it's also directly proportional. The greater the capacitance, the greater the amount of charge. On the other hand, as I shorten the distance, actually when I shorten the distance, the capacitance also gets greater because the strength of the electric field is greater. So I can increase, if I increase the distance, okay, that denominators, they're inversely proportional. I store less charge. So the closer these plates can get together without touching, the greater the amount of charge. Okay, so make sure you make some notes and play around with that idea. There's a good simulation for this on FET. There's a capacitor simulation on FET that you can go to right now and play around with to get an idea of the total charge stored and how these variables affect that total charge. All right, but now let's get to doing some calculations with these two formulas. Okay, so here's an example problem. That's from your Tsokos textbook. A parallel plate capacitor has plates of area 0.88 meters squared, separated by a distance of 4 millimeters in a vacuum. It's connected to a DC source with a potential difference of 6 kilovolts. Calculate A, the capacitance, B, the charge on one of the plates, C, the electric field between the plates, and D, the charge per unit area on the plates. So going through this together, or if you went through your text, you would know capacitance has two formulas, Q over V, and capacitance has this formula, which are in your data booklets. Okay, so which one can I use? They gave me area, they gave me the distance. The dielectric is not here, but I can search it up. It's a vacuum, so it's the permittivity of free space. Okay, so I'm gonna select this formula here because that's the value that I have. So to solve the capacitance, C is equal to, now to find the dielectric of free space, I'm gonna search in my data booklet, and I got something that looks like this, 8.85 times 10 to the minus 12 times the area, which is 0.88 meters squared, divided by 4 times 10 to the minus 3, because we're dealing with millimeters, is going to give me a value of 1.95 times 10 to the minus 9 farads. That's really, really small. In fact, that's 1.95 nanofarads. Okay? So that it would be NF on that capacitor that we saw at the beginning, a very small capacitor. Okay? So then what does that mean with respect to the charge on the plates? So I'll have to use this formula here, the charge of the plate, the charge on the plates. So once I've calculated the capacitance, I can jump to this formula. Capacitance times voltage is Q. So the capacitance times voltage is Q. Okay, so then 1.95 times 10 to the minus 9 farads times, I think it was 6 kilovolts, so 6,000 volts, gives me a value of 1.17 times 10 to the minus 5 coulombs. All right, so that's how many coulombs of charge are stored on one of the plates. Next question, the electric field. Well, this, we don't even need to know capacitors. We go back to the electricity unit. Electric field is the voltage divided by the distance separating the plates. So the voltage was 6,000 volts divided by 0.004 meters. Okay, that gives me 1.50 times 10 to the 6 newtons per coulomb. Okay, and the last question, which then says, calculate the charge per unit area on one of the plates. Okay, well, charge per unit area is going to be the total charge stored, which is 1.17 times 10 to the minus 5 coulombs, divided by the unit area, which is 0.88 meters squared, and we're left with 1.33 times 10 to the minus 5 coulombs per meter squared. Okay, after all these calculations, you now know how to use the two formulas for capacitance. You should know the definition of capacitance, you should know what all these variables are, and you should know how to play with both of these formulas. Usually you have to use one to calculate something in the other. That's a big exam trick. Okay, and paper one likes to play with dimensions of capacitors and asking what effect it would have on charge. So you need to be able to know how to relate this. Okay, they're directly proportional, so whatever I do up here is going to affect there, whatever I do down here is going to affect that. So play around with that in your mind, make some conceptual problems, and good luck with the first part of capacitors. The next part is we're actually going to put it into circuits and see how we can do some calculations with them.